Welcome back, guys. Today we'll be looking at a problem involving capacitors with dielectrics. Many of these types of problems deal with parallel plate capacitors, so to challenge us a little bit, I've chosen one with a little bit of a more untraditional geometry. Let's take a look at the problem statement. A spherical capacitor consists of two conducting shells of radii R1 equals 1 centimeter and R2 equals 5 centimeters, held at a potential difference of 120 volts. The capacitor is filled with two different dielectrics. The inner dielectric is a shell of silicon dioxide, whose dielectric constant is K1 equals 3.9. This shell has an inner radius 1 centimeter and an outer radius of 4 centimeters. The outer dielectric is a shell of Pyrex glass with a dielectric constant of K2 equals 4.6, of inner radius 4 centimeters and outer radius 5 centimeters. The first part asks, what is the capacitance of this spherical capacitor? And the second part asks, what are the total charges on the two plates? I've drawn the situation up here. This is a cross-section of the spherical capacitor. The outside conducting plate is here with a charge of negative Q, and the inside conducting plate is right here with a charge of positive Q. In between these two plates, we have two different dielectrics. In this region is silicon dioxide, and in the outer region right here is a Pyrex glass. So since we're asked to find the capacitance, let's first recall what the definition of capacitance actually is. It is the charge per voltage difference across these plates. So recall that a capacitor is when you have two conducting plates that are separated by some insulator or dielectric, and that insulator can be air or it can be some other material. Because you have charge separation, what that means is you're always going to have a voltage difference. Remember, when you pull two charges apart, there's a force and an energy that wants to bring them back together, which means that there's a potential that is inherent in that situation. In this case, it gives us that the voltage is 120 volts when you pull these guys apart. What capacitance quantifies is how much charge can you hold volt for volt. And it depends entirely on the geometry of the situation, and it also depends on what the capacitor is made of. Some situations can hold capacitance, they can hold charge much better than other situations can. And also, if you have different materials, they can hold charge much better than other situations can. So keeping all this in mind, let's go ahead and solve the problem. The first part asks us to find the capacitance of the spherical capacitor. Now we know that the voltage is actually 120 volts, so if we knew the charge, we could divide out and find out the actual number. It would be very simple. But we don't know the value of the charge. So instead what we can do is we'll keep in mind the fact that voltage itself depends on the actual charge itself, and it's typically proportional to these type of problems. So what we're going to do is find an expression for the voltage in terms of charge, and as an intermediate step we have to keep in mind that voltage depends on the electric field. So the plan for the problem will be the following. We'll first find the electric field. Now keep in mind, this is a situation in which the problem is highly symmetrical. So how do we solve for electric fields where it's highly symmetrical? We use Gauss's law. So the first part will be to use Gauss's law. Using that, we'll then find the voltage difference across the two plates. And that equals the path integral between the first plate to the second plate. And then lastly, once we know this, which we expect to be proportional to Q, we'll divide it out to find out what the capacitance is. And the capacitance will not depend on Q because it'll divide out. Again, it only depends on the material properties, so all you'll be left with is something that depends on the radii and the dielectric constants. So the last part is just divide out these two portions. So let's go ahead and get started. The first thing we have to do is find the electric field. So let's go ahead and just write down I'll just say the electric field, let's say use Gauss's law. To find the electric field. Typically when we use Gauss's law in the past, we used it to find electric field where there was only a vacuum and there was no materials inside. In this case, we have a dielectric. So to use the fact that we have a dielectric, it's actually pretty straightforward. We just find the field as if it were vacuum, using Gauss's law. And then the field inside the dielectric is going to be that field divided by the dielectric constant. So I'll say it equals the field in vacuum divided by the dielectric constant. In cases where you have a high dielectric constant, the field is heavily reduced because you're dividing by a larger number. So what I want you guys to do is go ahead and do this on your own. Find out what the field is in regions 1 and regions 2, which I'll just denote up here. Blue, so this is region 1. And this is region 2. And what you want to do is find the field using Gauss's law first, and then just divide by the dielectric constant in those respective fields to find out what the actual field is there. but you want to find it in terms of the charge on the plates, the distance from the center, so the radial distance, and then the respective dielectric constants. So again, use Gauss's law to find the field, divide by the dielectric constant to find the actual field here in the presence of the dielectric. Go ahead and take a minute now, pausing the video if you need to. So what you should have gotten for the fields is the field on the inside is equal to Q divided by 4 pi epsilon naught times the dielectric constant, and it's inversely proportional to the radial distance squared, and then likewise for the field on the outside. Note that with Gauss's law, you would have got the exact same thing without the dielectric constant. So just to get the field in the presence of the dielectric, you just divide by the dielectric constant. Now, since we're looking for capacitance, we need to use these to find the voltage potential difference between the inside and outside plates. And so we have to integrate these along the path from the inside plate to the outside plate. And because we have two different fields, we have to break up the integral into two regions. One for the silicon dioxide portion, and we're going to integrate E1 there because that's what the field is there. And then one for the Pyrex glass portion where we're going to integrate E2 because that's what the field is in that region. Go ahead and get an expression for this in terms of all these quantities. Not a numerical answer, but just an expression. And take a minute to do that now. Pause the video if you need to. So what you should find for the potential difference is the following expression. It's given by Q over 4 pi epsilon naught, and then you're going to have these geometrical factors on the inside along with the material properties there. So this is from the first integral, and then this factor is from the second integral. All right, so finally we're looking for the capacitance, so we divide this into the charge. And so Q divided by this delta V means, as expected, the voltage is proportional to the charge, so when we divide it out, the charge cancels. Now what we're left with is a quantity that only depends on the material properties and does not depend on how much charge or voltage is across this capacitor. So this is the final expression for the capacitance of this spherical capacitor. And you can find a numerical answer for this if you'd like using the values given in the problem. The actual numerical correct solution is given online, is given on the link next to the video link. And you can also check all the algebraic steps in between there if you'd like. Finally, for part B, what we're looking for is the charge that would be held on this capacitor if the voltage across the two plates was 120 volts. So now that we know the capacitance, which is a fixed quantity and is independent of what charge is on here, we can treat that as a fixed number and solve this guy for Q to get that Q equals the capacitance, which is fixed, times, in this case, 120 volts. And once you get a number for this guy, you can plug it in here and find out the actual charge on here. And again, that's also given on the written up solution that's attached to this video. So let's summarize what we've done here. In this problem, we were given a spherical capacitor with two embedded dielectrics. First, we found the electric field in each region using Gauss's law. Then we integrated the field in two parts from plate to plate to find a symbolic expression for the potential difference across the plates. To solve for the capacitance, we divided the potential difference into the charge canceled, and we were left with an expression only depending on the material properties and geometry of the capacitor. For part B, we found the charge on the capacitor when it held a potential difference of 120 volts by using the capacitor equation. So that'll do it. And I hope this video was a useful example of how to approach capacitance problems, particularly those involving things like dielectrics and non-standard spherical or cylindrical geometries. Please feel free to leave some comments and helpful feedback on the link accompanying the video, and we'll see you guys next time.